So welcome to chapter 4. We're going to start talking about probability here in chapter 4. We'll continue this discussion in chapter 5. Now, probability is something that we all have some familiarity with. We all have some experience with it. It's something that's taught in math from grade school on up, whether you flip a coin or roll a die or something like that. So we have some familiarity with probability, but we're going to talk about some specific components, or rather some specific terms that we use with respect to probability when we're conducting statistics. So really this first unit is kind of defining a lot of these terms that we may or may not be familiar with, and we may or may not be familiar with in this specific meaning. As I've mentioned before, I'm an accounting professor, and one of the things I teach my accounting students is that we use a lot of terms in everyday language that means something different in accounting, and that's similar to what we're going to see here in probability. There's going to be a lot of terms that we know the term kind of in our normal everyday life, but it has a little bit different meaning when we use it in a specific statistics setting. So the first thing that we're going to talk about is just what is a probability. A probability is just a numerical value that measures the likelihood that some event is going to happen, right? So whatever the probabilities are between 0, as in it is definitely not going to happen, to 1 where it is most definitely, think of it as 100% going to happen. And oftentimes we will state probabilities in terms of percentages, although they don't have to be. So anything that has an uncertain outcome has a probability. And this applies to anything in life, right? So you let's say you get sick, not COVID, maybe you just have a headache, you take some leave. There's a probability that that's going to fix your headache. I mean, it may be a high probability, but it's uncertain, right? It's possible that you could take some leave or aspirin or whatever it is you prefer to take, and it doesn't fix it. So there's a probability there that we could, if we wanted to, numerically assess what is the likelihood that taking this medication will fix our headache. So when we talk about an experiment, I'm sure most of us kind of think back to maybe our science, our high school chemistry classes, and we're mixing chemicals and we're blowing things up, and that is certainly an experiment, but in statistics, that doesn't have to be an experiment. And in statistics, an experiment is really just kind of whatever our question is, right? It is the thing that leads us to one of any possible outcomes. So an experiment is anything that's happening that we're questioning, hey, what is the possible outcome? And there's more than one possible outcome here. So the experiment could be, hey, if I take this medication, will it make my headache go away? Or maybe the experiment is, if we make this earnings announcement, what will happen to our stock price? Or maybe the experiment is, if we buy this advertising package, what will happen to our sales, right? So any question that we have like that that has multiple outcomes is really what we're calling our experiment, okay? So we're going to kind of follow along with the experiment that the book talks about, which really isn't business related, but I'll throw in some business questions as we go along here. So we have a snowboarder who is competing in the Winter Olympic Games in the ladies half pipe event, and they're trying to say, this is the experiment, is, you know, what's going to happen, what's going to be the outcome. So she could win the gold medal, the silver medal, the bronze medal, or no medal at all, right? So the sample space, which is marked with a capital S. Remember, a small s is our sample, or standard deviation. So the large S is our sample space. This is all the possible outcomes of the experiment. So going back to our snowboarder, all the possible outcomes could be gold medal, silver medal, bronze medal, no medal, right? Talking about the headache experiment, the experiment could be, the possible outcomes could be my headache goes away, my headache doesn't go away, or my headache is lessened in severity but doesn't go away, right? And we can define for ourselves what that sample space is, what all of those possible outcomes are. So For example, if you're talking about a letter grade on a test, you could maybe do it as A, B, C, D, or F, right? That could be your sample space. So the event is the actual what happened, right? So the event is you took the test, you get a B, or you participate in the event and you get the silver medal, or you take the aspirin or the Aleve or the medication or whatever, and your headache goes away, right? So the event is really like the individual subset of the sample space. So again, the sample space is all the possible outcomes. So we talked about here that our sample space, going back to our half pipe winter of snowboarding event, is we could get the gold medal, or she could get the gold medal, the silver medal, the bronze medal, or no medal. You could define your sample space as something else. Maybe you choose to define it as first place, second place, third place, fourth place, fifth place, or worse than fifth, right? So you could define your sample space however you choose. So when we talk about events, events can be either exhaustive, mutually exclusive, or both. So an event is exhaustive if all of the possible outcomes are listed as a possible event, right? So if we talk about earning a certain grade on the test, the only options are an A, a B, a C, a D, or an F, right? It's not possible to make any other grades. So if that would be an exhaustive list of events, right? Whereas if we're talking about the skier and we define our events as medaling or not medaling, I mean, that's exhaustive, but it is possible that maybe she doesn't even finish the race. Maybe she has to get scratched. Maybe she is disqualified. So that could be a third event that's not listed, that's not taken into consideration. So as we start constructing our experiments, and we'll get into this kind of again more in later chapters, again, we're still kind of laying that framework. We want to try to think of and list all of the events that are possible to make as exhaustive of a list as we reasonably and possibly can. Now, events are said to be mutually exclusive if they can't overlap, right? So either you made an A on a test or you made a different grade, but it's not possible to make an A and a B on the same test. So our grades on a test is exhaustive because mutually exclusive, pardon me, because you can't overlap events. The events can't overlap, right? Whereas if we're talking about medaling in an event, well, we could say, well, if you make at least if you medal in the event, then that could be a gold, a silver, or a bronze. So those events could overlap. They're not necessarily mutually exclusive. So I know that we're all familiar with a Venn diagram where the box is our sample space and then the circles are our event outcomes. So we've got a simple one here where we only have two event outcomes, A or B. So the union is the event consisting of all the simple events. So we could say this as A or B. What is the probability of getting an A on the test or a B on the test? Or what is the probability of winning the gold medal or the silver medal? Okay, so what is the probability of A or B? And so we identify this union as like this U shape here, but you want to read that as A or B. So the intersection is where the two circles cross. So think of it as it's this area right here that I'm kind of coloring in black. So we denote that with like that upside down U. So we would read that as that's the part where A and B occur. Now the complement of the event, which we're going to denote as A superscript C, is the event consisting of all the outcomes in the sample that are not A. So you took the test, all the possible outcomes that are not making an A on the test. So B, C, D, or F are the complements of A. So let's go through an example. Remember that snowboarder, we defined the sample space as gold, silver, bronze, or no metal. And then let's look and see if we can find the union, the complement, the intersection, and then the complement of B. So A is defined as getting a gold, silver, or bronze medal. B is defined as getting a silver, bronze, or no medal, so everything except getting the gold. And then C is defined as no medal at all. So these are how we've defined our events here, right? So our events are defined as A is getting a gold, silver, or bronze, B is not getting a gold, basically everything else, and C is not getting a medal at all. All right, so remember that our sample set is gold, silver, bronze, or no metal. So first we're going to look at the union of A and B. So remember A was getting a gold, silver, or bronze. I'm going to write this up here at the top because I tend to forget. So A is gold, silver, or bronze. B is silver, bronze, or no metal, where C is no metal. So the union is looking of A and B is looking at all the possibilities that exist between A and B. So A covers gold, silver, and bronze, and B covers silver, bronze, and no metal. So the union of A and B is the four possibilities of gold, silver, bronze, or no metal. So there's no double counting. We don't double count the silver and bronze. They're in both A and B, but we're not double counting them. The union is just all the possible outcomes with those two events. So then we were asked to calculate the union of B and C. So B and C is silver, B is silver, bronze, and no metal, and C is just no metal. So the union of those is just silver, bronze, and no metal. In fact, all of C is contained inside B, but gold is not one of the options under the union of B and C. So next we were asked to find the intersection of A and B. So where do A and B cross? So A and B, the intersection of A and B are silver and bronze. This is where these two cross, where they intersect, if I were to diagram them. The intersection of A and C, though, is none. There's not an intersection of A and C. A and C don't intersect at all. If I were to draw those two circles, they would never touch. Okay? They would never touch. And then lastly, we were asked to find the complement of B. So the complement of B is everything that is not included in B. So B includes silver, bronze, and no metal, but it does not include gold. So the complement of B is winning the gold medal. Now I know this can be a little bit confusing, but again, if you'll draw those circles and kind of draw those out on your notes, it might help you make sense of it. So remember we said that the probability of any event occurring is between 0 and 1, where 0 is it's most definitely not occurring and 1 is it most definitely is occurring. So if we look at the sum of all of the probabilities for all events in an experiment, they will add up to 1. So when we assign probabilities, there's two ways that we do this. A lot of times we do this just subjectively. Subjectively is our personal opinion. Maybe it's based on past experience. It's based on, kind of how we're feeling at the time. Are you optimistic? Or are you pessimistic? But it is purely subjective. Okay. Whereas objective probabilities have an empirical data given to them, right? Now, in order for something to be an objective probability, the experiment has to be repeated a large number of times to be accurate. Okay, you can't just flip that coin 5 times and say, well, the probability of it hitting tails is 60%. Okay, you have to flip it a large number of times. Now, what's a large number of times? Well, that depends. And we'll talk about that a little bit later as we get into further chapters and we start talking about sample sizes and things like that. But really, a very large number of times, right? We're not just going to do this a couple of times or base it on a couple of observations. So the probability of a frequency of a particular event occurring, which we call P and then the A is the event that we're measuring, so the probability of A occurring is the number of outcomes in A and divided by the number of outcomes in the entire sample. So given these probabilities that we're told here, the probability of winning a gold medal, a silver, a bronze, or no medal, we can identify the probability of a certain event occurring as the probability of the gold plus the probability of the silver plus the probability of bronze. Where remember A, what we defined as event A, was winning a gold, silver, or bronze. So we can calculate the probability of winning that medal by adding up the probabilities of the gold, silver, or bronze. So when we add those up, we determine that the probability of winning a medal is 45%. The probability of winning the gold medal is only 10%, but the probability of winning any medal is 45%. So the probability of the union of B and C would be the probability of silver plus bronze plus no medal, which would add up to be 90%. Or we could say the complement of B, so the complement of not winning the silver, bronze, or gold medal would be 90%. And then since the probability of getting a medal or no medal, there's no common outcome, so there's no intersection there. And then here I jumped ahead. The probability of the complement of B, which means the probability of winning the gold medal, is 10%. So looking at this example, here we're given some data of the richest 400 Americans and what their age is and how the frequency of people that fall into that category. And then we've calculated the relative frequency. So we have 400 people total. The sum down here is 400. And so we can determine that the probability of C, the probability of one of the richest 400 Americans being between the ages of 50 and 60 is 16.75%. So we could say the probability of one of the richest Americans being under 40 or up to 60, but 60 or younger, is the probability of them being under 40, the probability of them being under 40, plus the probability of them being 40 to 50, plus the probability of them being 50 to 60, or 26%. So the probability of them being 80 or above is the probability of them being 80 to 90, or 90 and above, or 16.5%. And I'm just converting these to a percent by moving the decimal 2 places to the right and tacking a percent sign on it. Certainly you do not have to convert them to a percent. We don't always convert them to a percent. It's just that we're comfortable talking about percent.